Dissociation, in particular dissociation equations, and then doing a little math with them will be our theme now. So what is dissociation? Okay. Not all solutes dissociate. So eventually you'll be assessed on, what compound would dissociate. Okay. This is just when we have the separation of cations and anions. So when a highlight is not written there, we're not making ions. You have to have ions already, and they just come apart. Okay? If you make ions from something neutral, okay, you remove electrons, that's ionization, that's next. Okay? So you're going to see dissociation happen with ionic compounds. When you have cations and anions already, those are your metals and non-metals in most cases. Okay? Or polyatomic ions that are positive and negative. Dissociation equations represent this coming apart in water. So I've already written out a dissociation equation, that's separation. Now, one thing that can be a little confusing is just water doesn't show up as a chemical. Okay? You might, in words, be told magnesium chloride is put into water, write the dissociation equation. Okay? Water is the solvent, and it's just showing up in our state. Okay? Don't go magnesium chloride plus water is magnesium ion and chloride ion. Okay? Now, I really want to take a minute to explain this notation. Now, in explaining it, I'm going to write some things that I would never ask you to do on a test or quiz. But I want to make sure you have a good mental picture of what's going on here. It's really not what the notation shows. Okay? We write the positives and negatives grouped together. There's one magnesium 2+, and there's two chlorides in the ionic compound. Okay? But that's really a repeating pattern. You're going to have a magnesium 2+, and two chlorides aren't going to be next to each other. They're going to be stuck to it, but they're going to be apart from each other. Okay? Now, that's just a linear projection of that molecule. In real life, the magnesium and the chlorides are spread out in all three dimensions. And you see a repeating 2-to-1 ratio throughout this solid. Okay? And it's a whole study of ionic compounds in university. Okay? They can actually deflect X-rays, shoot X-rays at ionic compounds and see how the X-rays scatter to figure out where the atoms are and what their shape is. Okay? But the two chlorides are next to each other. They would repel. But they're all stuck together. They're a solid. You put them in water, and they're no longer a solid. They're going to be surrounded by water. We're going to have this aqueous solvent. So trying to give you a visual of that would have magnesium 2+ ions, and then you're going to have water molecules all around them. Now, to draw my waters, we haven't studied it yet, but water looks like that. And to make these notes faster, I'm just going to do a little kind of upside down V to mean the water. Okay? It's faster, it makes cleaner notes. So water is H2O, there's two H's, there's an O in the middle. Okay? And you're going to see water molecules surrounding this. I'm going to do a flat projection in 2 dimensions, but there'll be a water on top and a water behind. Okay? The chlorides are gone. They're somewhere else surrounded by water. Okay? So that's my magnesium aqueous surrounded by water, and we would have chloride aqueous, and it's also surrounded by water. Now we'll dive into it later. The water actually flips around, and the other end of water is attracted. Water is a polar molecule. There's a positive end and a negative end that'll be attracted to ions differently depending on their charge. So that'd be one of the chlorides. The other chloride is also totally separate and surrounded by water. So where they were attached to the magnesium at the beginning, they're now totally separated. So in the magnesium chloride formula unit, the convention is if there's more than one ion, you write it as a subscript because it's all locked together. Okay? We can't put the 2 in front because it would double everything. When we get to our dissociated ions, the chlorides are now nowhere near each other. They're totally separate. They're surrounded by water. There just happens to be 2 of them. And we don't write it as a subscript anymore. We put it in front. There are 2 chlorides surrounded by water, separated out. For every 1 magnesium chloride, you're going to have double the amount of these separate chloride ions. This causes a bit of confusion. Why do we use a subscript in magnesium chloride solid and we put the 2 in front when we break them apart? Okay? It's to show that fundamentally the chloride ions are separated and we're just doing a count of how many we have. Okay? So this bottom blue and green is not something you do on a test, but I want you to have a good understanding of what's going on with that notation. Okay? A second example, I'm not going to do out all that blue and green. Sodium carbonate is an ionic compound. It can dissociate. We've got sodium plus, carbonate is a 2 minus. Only ever break into 2 pieces because an ionic compound that's going to dissociate already had a cation and already had an anion. It's never going to have like 2 different positives and 1 different minus, or 2 minus pieces and 2 positive pieces. If you've got a metal, they should be fairly straightforward. You're just going to break between the metal positive and the negative piece. In this case, it's a polyatomic. That subscript for the sodium, when everything breaks apart, pops in front. So there are 2 sodium aqueous ions and 1 carbonate aqueous ion in solution. The presence of these aqueous ions is what makes something conductive and would make it an electrolyte. If you put something in water and it doesn't make any ions or separate out any ions, it would be non-conductive. If you put sugar in water, it doesn't do this. We don't see any ions formed. Okay. So it's the aqueous as well as the charge. We need those 2 pieces to make our solutions conductive. So we're going to do a little bit of stoic. Once you can write a dissociation equation, we can make predictions. For every 1 unit of the solid that we put in, we're going to get double the sodium ions. So if we know some concentrations, we can apply that doubling or tripling or no change 1-to-1 ratio with our concentrations. So concentration of ions, really concentration of aqueous ions. I just didn't write out aqueous. And I'm going to determine the concentration of all ions in a 0.5-ish mole per liter calcium chloride solution. So the first thing to answer this, you have to have the dissociation equation. You might do this in your head on a test, but while you're learning, I would write it out. So sodium chloride, solid, is your solute. It was put into water. Both ions have a charge of 1. So this dissociation equation doesn't have any stoichiometric coefficients above 1. These stoichiometric coefficients, which we typically don't write, are 1, 1, and 1. Okay. This question is saying at the beginning, there are 0.52 moles of solute put in every liter. and then it's going to start breaking up and coming apart, and that number might change. For sodium ions, okay, we can do our required over given prediction. Okay, you get 1 sodium ion for every 1 sodium chloride unit that's put in, so it's the same number. Okay, so the sodium ion is the same concentration as the ionic compound that was put in at the beginning. Chloride, it's going to be the same thing. I'm not going to write out the math again. It's 1 chloride for every 1 sodium chloride. Multiply by 1, divide by 1. So there's about a half a mole. I don't do it very often as a quiz question, but I could ask, what's the total concentration of ions? Where you just add the 2 green numbers together. There's actually over a mole of ions. Okay. Half a mole-ish of sodium, half a mole-ish of chloride. That one was a little, we had no coefficients, none of the concentrations changed. That won't be the case here. What's the concentration of ions in about a 1/4 mole per liter calcium chloride solution? I'm going to write the dissociation equation first. We have calcium in group 2, which is Ca. We have chloride in group 7A or 17. I'm going to switch to red. You don't have to write the charges. You just have to have the right subscripts. So you have to realize that's a 2+ ion. That's a -1 ion. You can write it out or you can do it in your head. I'm going back to blue because you must show that you need 2 chloride ions to balance the 1 + 2 calcium. So now we can write our dissociation equation. When this breaks up, we only get 1 calcium ion in solution, but we will have 2 chloride ions separated apart from each other. We're going to get a doubling of the chloride concentration. So I have that 0.24 mole per liter original concentration of solute put into total solution. Calcium, no coefficients, they're both 1s, so that's going to be the same concentration. One to 1 ratio between those species. Now, when we go to chloride, it's a little different. We've really done this already in Stoich. Okay. We're going to form 2 chloride ions for every 1 calcium chloride we put in solution. So 0.24 times 2 divided by 1. 0.48 moles per liter. Okay. So not that difficult. This is as hard as it could get, and you're really just applying stoichiometry. 0.1 mole per liter, aluminum carbonate. We're going to have to do a little lowest common multiple to get our subscripts here. We have an aluminum from group 3. Now it's a metal. It's about as far over as you can get and become a metal without dropping lower in our periods. Aluminum is a 3+ charged metal. Carbonate is a polyatomic ion, CO3, and your table tells you it's 2-. So we have a +3 and a -2. There's no one step to balance those out. So you think lowest common multiple and scale them both up to it. So 2 and 3 repeats at 6. So I'm going to need plus 6 and minus 6. I'm going to need 2 aluminum to get plus 6. Carbonate is minus 2, so I need 3 of them, minus 2, minus 4, minus 6. It's polyatomic, so when I triple it, I have to triple the whole thing, the whole minus 2 ion. So that is aluminum carbonate. We put that into water, which doesn't show up as a reactant anywhere. So we're going to get aluminum ions. How many of them? Well, there were 2 at the beginning, so we're going to get 2 separate aluminums. Then we have our carbonate. When that all breaks up, there are 3 of them in the original formula unit, so we're going to get 3 of them. Okay. Now, one thing I've been doing is I've been ignoring solubility. So I've been assuming everything has been soluble, which isn't always the case. But that's one thing I've been sort of not checking as I go through this. So now if we have 0.10 moles per liter, let's kind of just do it visually. The original formula unit to the aluminum is a double. We got 2 aluminums for every 1 at the beginning. Okay. So most aren't going to do the required over given. Hopefully do this visually. We get double the concentration of aluminum compared to the beginning. The carbonate is 3 compared to 1 coefficient at the beginning. That's a triple. So you triple the original formula unit. So 0.2 of aluminum, 0.3 of carbonate. Okay. And you're not going to get anything more complicated than a subscript on both. Okay. So now we want to practice this. We've learned about dissociation. Ionization is next, followed by Arrhenius acids and Arrhenius bases.